Alright guys, in this video we'll take a look at problem number 2 from off the group quiz that we worked on for section 2.8. And this was a question where we had this relation defined implicitly, and we just wanted to try to find all horizontal and vertical tangents. So a horizontal tangent is just going to imply that the slope of the tangent line is 0, or the derivative is 0, and then vertical tangent would mean the slope of the tangent line is undefined. So we have a little bit of work to do here. Since we're looking for tangent lines, we need to find the derivative because slopes of tangent lines are determined by values of dy dx, or values of the derivative. So we need to quickly try to compute the derivative of this, and we're going to do it implicitly. And whenever we use implicit differentiation, we're always assuming that y is a function of x. So when I do the derivative of the left side of the equation, the derivative of x squared is 2x, but then since y is a function of x, I have an inner function y, outer function something cubed. So I'm going to do the derivative of the outer function, which would be 3 something squared. The something has to be the inner function, and then I need to finish the chain rule by multiplying by the derivative of the inner function, and the derivative of y with respect to x would be dy dx. Then I'm going to have minus 3 times the derivative of y, and the derivative of y with respect to x is dy dx. And then the derivative of 4 on the other side of the equation is 0. And then just like we've done in class pretty frequently, we want to go ahead and try to see if we can isolate dy dx. So this term does not have a dy dx on it, so we'll move it to the right side of the equation. I have these two terms left, both of which contain a dy dx. So I'm going to factor dy dx out as a common factor. And then I'll be able to solve for dy dx, or solve for my derivative, by dividing each side by this quantity. So dy dx is going to end up being the negative 2x that I already have over here divided by this set of parentheses. So negative 2x over 3y squared minus 3. So there's dy dx. We were finding this so that we could figure out where this relation had horizontal tangents and vertical tangents. I'll deal with the horizontal tangents first. If I'm going for horizontal tangents, I know that the slope of my tangent line would have to be 0, and so I know that dy dx would have to be 0. So now we need to figure out when dy dx equals 0. Does it ever happen? Well, look at dy dx. It's a fraction, and if this fraction's numerator is 0, as long as the denominator is also not 0, then dy dx is 0. So it's pretty simple to say dy dx is 0 anytime negative 2x equals 0, or anytime x equals 0. So we know that anywhere on this relation where x equals 0, dy dx is going to be 0, and we're going to have a horizontal tangent. So now we need to figure out where on this relation x actually equals 0. So I'm going to take the relation, bring it down below, and I'm going to put 0 in place of the x. So I'm going to put 0 in place of the x, that gets squared, plus y cubed minus 3y equals 4. If I can solve this equation for y, I'll then know where on my curve I have the horizontal tangent. I know it's when x is 0, but what's my y value? Well, the y value is going to be whatever the solution of this equation is. Now, we haven't seen many equations like this. This is an equation that you can't really solve by factoring. You can consider doing that if you subtract 4 from each side and get it set equal to 0. But then how are you going to factor this thing that has the y cubed in it? It's going to be pretty difficult to do that. So this one, in class I mentioned this to everybody, this is something I would solve graphically on the calculator. So if I want to solve this graphically, I want to graph what I have here and figure out when that graph is equal to 0. So to do this on the calculator, I'm just going to have to type in, let me see if I can get this on here. So I'm going to have to type in, I can't type in y cubed, I'm going to have to type in x cubed minus 3x minus 4. If I graph this, I'm going to look for where the other side is 0, so where y on the graph here is 0. So I'm graphing, and then there's only one spot on the graph where y is 0, happens right here, so it seems like it's about 2. Don't estimate it, go ahead and have the calculator find that for you. So grab the 0 feature, your left bound, there's good, right bound, good, guess, there you go. So we get next value of 2.196, I'll round that to 2.196. So y would be about 2.196. So on this relation, if we had the capability to graph it, and I'll actually show you this graph in a little bit once we do the vertical part of the problem, we should see that the graph has a horizontal tangent line at 0, 2.196. So where do we have horizontal tangents? 0, 2.196. The vertical part of this problem is going to be a little bit trickier to do. We're going to have to take our derivative still, and we're going to have to figure out where it's undefined. So this fraction's undefined when the bottom is 0. So I'm going to flip over to the back of the page here, and I'm going to, for the vertical half, figure out when this denominator, which was 3y squared minus 3, I'm going to figure out when that's 0, because when that's 0, my derivative would be undefined. And this is something that you can solve by factoring. You can factor out a GCF of 3, and you have y squared minus 1. That's a difference of 2 squares, and a difference of 2 squares is always going to factor to an expression like this. The reason why I prefer to solve this by factoring, I noticed in class people who solved it by isolating the y, adding 3, dividing by 3, then taking the square root. A lot of people did not get the solution of y equals -1. They just got the solution of y equals +1. So there are two values of y that make our derivative undefined. They're 1 and -1. So anywhere on our graph where y is equal to 1 and y is equal to -1, we're going to have vertical tangents. But what are the x values on this graph where we have these vertical tangents? So that's why we need to go back to the relation one more time, and that relation, I'll just kind of copy it down in the corner here, was x squared plus y cubed minus 3y equals 4. Just let me double check and take a peek. So x squared plus y cubed minus 3y equals 4. Yeah, that's what I copied down. So I want to figure out where on the graph of this relation y is 1 and where on the graph of this relation y is -1. So we'll do the y equals 1 part first. I'm going to take 1, I'm going to put it in place of the y's in the relation, and I'll be looking at x squared plus 1 cubed minus 3 times 1 equals 4. And if you simplify this, that's just a +1, that would be a -3. Combine those and you're looking at -2. Move that across and you have x squared equals 6. And if you take the square root of 6 to solve this, the one thing that you can't forget to do, and I mentioned this a couple minutes ago, one thing you can't forget to do is that symbol out in front. There are actually two values of x that would make this equation right here true. The positive square root of 6 squared is 6, and then negative square root of 6 squared would be equal to 6. So we actually get 2 points on the curve where y would be equal to 1. The x values would be positive square root of 6 and negative square root of 6. So I'm just going to jot these ordered pairs down. So we have one vertical tangent at 1 comma square root of 6. We have another vertical tangent at 1 comma negative square root of 6. Now we did get a second y value that made the derivative's denominator 0, or made the derivative undefined. So I'm going to also do the same thing with that y value. So where on the graph of the relation is y equal to -1? So I'm going to put -1 in place of